So here's something to think about as you settle in tonight. Right now, as you're lying there, probably with your eyes half closed, there are roughly 4 billion devices around the world running some form of artificial intelligence. Not the kind you see in movies, not a glowing red eye or a silver robot. Most of it is invisible. It's the thing that decided which emails you saw today and which ones got quietly buried. It's the system that approved or denied someone's loan application this afternoon in about 11 milliseconds. It's the algorithm that figured out you were probably going to enjoy that song it recommended last week. And honestly, it was right, wasn't it? That's the strange world we're living in now. And the story of how we got here, how we built minds out of math, and what those minds are doing that we didn't quite expect. That's what we're going to wander through tonight. Let's start with something genuinely unsettling, but in a quiet way. The first serious proposal for a thinking machine wasn't born out of optimism. It came out of war. It was 1943, and a neurophysiologist named Warren McCulloch and a young mathematician named Walter Pitts published a paper with the dry title, A Logical Calculus of the Ideas Immanent in Nervous Activity. Not exactly a page-turner of a name. But what they proposed was radical. They said you could model the neurons in a human brain as simple on-off switches, logical gates, and that a network of these artificial neurons could, in theory, compute anything computable. They were describing the basic architecture of a brain using the language of machines. Now, Walter Pitts is worth pausing on for a moment because his story is one of the saddest in the history of science. He was essentially self-taught. He grew up in poverty in Detroit, and the story goes that as a teenager, he wandered into a library to escape bullies and found a copy of Bertrand Russell's Principia Mathematica, one of the densest, most forbidding works of mathematical logic ever written. And he just started reading it. He found errors in it. He wrote to Russell about them, and Russell was so impressed that he invited the kid to come study at Cambridge. Pitts didn't go to Cambridge, but he did eventually end up at the University of Chicago, sleeping in the library stacks, attending lectures he wasn't enrolled in, and somehow producing foundational work on neural networks before he was 20 years old. He died at 46, largely forgotten, struggling with alcoholism. The man who helped imagine artificial minds couldn't quite navigate the world that real minds had built. And that tension between the elegance of the theory and the messiness of reality runs through this entire story like a crack in a foundation. So McCulloch and Pitts gave us the idea. But the person who really lit the fuse, the one whose name you probably know, was Alan Turing. In 1950, Turing published a paper called Computing Machinery and Intelligence, and in it he posed a question that still haunts us. Can machines think? But here's the clever thing Turing did. He knew that thinking was a word people would argue about forever, so he sidestepped the whole philosophical mess. Instead, he proposed a game. Put a human in one room and a machine in another. Let a judge ask questions to both through a text interface. If the judge can't reliably tell which one is the machine, then for all practical purposes, the machine is thinking. That's the Turing test. And what's disturbing about it, what's really worth sitting with, is that Turing wasn't saying the machine would actually be conscious. He was saying it might not matter. If you can't tell the difference, what's the difference? Think about that for a second, because we're living in the answer to that question right now. There are chatbots today that can fool people in casual conversation. Not all the time, not under rigorous testing, but often enough that the line Turing drew in 1950 is getting blurry. And the strange part is that these systems don't work anything like the way Turing imagined. He was thinking about logic, about symbolic reasoning, about a machine that would essentially argue its way to intelligence. What actually happened was something much weirder. But we're getting ahead of ourselves. Let's go back to the beginning of the real engineering. The summer of 1956 is when artificial intelligence officially became a field. And it happened. At a workshop at Dartmouth College in Hanover, New Hampshire, a young mathematician named John McCarthy, he was only 29, convinced the Rockefeller Foundation to fund a 2-month summer research project. The proposal he wrote included this remarkably confident sentence: "Every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it." Just think about the audacity of that. He was saying, essentially, that intelligence is an engineering problem. Figure out the specs, build the machine, done. The people who showed up to that workshop read like a roster of future legends. Marvin Minsky was there. He'd go on to co-found MIT's AI lab. Claude Shannon came, the father of information theory, the man who had essentially invented the mathematical framework for all digital communication. Nathaniel Rochester from IBM attended. Herbert Simon and Alan Newell, who had already built a program called The Logic Theorist that could prove mathematical theorems. And here's a detail I love. The workshop was kind of a mess. People came and went. There wasn't much structure. They argued a lot. Most of them were working on completely different approaches and couldn't really agree on anything. But the name stuck. McCarthy coined the term artificial intelligence, specifically for this workshop, and it's the name we've been using ever since. He later said he wished he'd called it something else, because the word intelligence promised too much. It made people think of human intelligence, of consciousness, of understanding, and the machines they were building didn't understand anything at all. Here's the first truly disturbing fact buried in this origin story. From the very beginning, the founders of AI dramatically underestimated how hard their project would be. Herbert Simon predicted in 1957 that within 10 years, a computer would be chess champion of the world. It took 40 years. Marvin Minsky said in 1967 that, within a generation, the problem of creating artificial intelligence will substantially be solved. We're 3 generations past that now, and we still argue about whether we've solved it or whether we've built something that just looks like a solution. The pattern of overconfidence in AI is not a bug in the field's history. It's a feature. It keeps happening. Every decade, someone announces that true AI is just around the corner. And every decade, reality turns out to be more complicated than anyone thought. But those early years were genuinely exciting, in the way that the first few miles of a road trip are exciting, before you realize how far you actually have to drive. The programs they built in the late 50s and early 60s were simple by today's standards, but they felt like magic at the time. Newell and Simon's logic theorist could prove theorems from Principia Mathematica, the same book Walter Pitts had read as a teenager in that Detroit library. Their next program, the General Problem Solver, could work through simple puzzles using means-ends analysis, basically breaking a problem down into the difference between where you are and where you want to be, then finding operators to reduce that difference. It sounds obvious when you describe it, but encoding that kind of reasoning into a machine in 1959, on computers with less memory than the chip in a modern greeting card, was genuinely remarkable. And then there was ELIZA. This is one of my favorite stories in all of computer science. In 1966, Joseph Weizenbaum at MIT created a program called ELIZA that simulated a Rogerian psychotherapist. If you've never encountered Rogerian therapy, the basic technique is to reflect the patient's statements back at them as questions. You say, "I'm feeling sad," and the therapist says, "Why do you think you're feeling sad?" ELIZA did exactly this, using simple pattern matching. It had no understanding of language, no model of psychology, no knowledge of the world. It was basically a very clever parlor trick. And here's what disturbed Weizenbaum so deeply that it changed the course of his career. People knew Eliza was a program. He told them it was a program. He showed them the code, and they still formed emotional attachments to it. His own secretary asked him to leave the room so she could have a private conversation with Eliza. Students would sit with the program for hours, pouring out their feelings, even though they understood intellectually that they were talking to a few hundred lines of code. Weizenbaum was so shaken by this that he spent the rest of his life warning about the dangers of artificial intelligence, not because the machines were too smart, but because humans were too willing to believe they were. We project consciousness onto things that have none. We see minds where there are only patterns. And that vulnerability, that deep human need to find someone listening on the other end of the line, is something that every AI system built since then has exploited, whether intentionally or not. Think about that the next time you catch yourself saying "thank you" to Siri, or apologizing to a chatbot. You know it's not real. You know there's no one there. But something in you responds as if there is, because 100,000 years of evolution built you to detect minds, and you'd rather find a mind that isn't there than miss one that is. That's the first crack in the wall, and it opened in 1966. Now, the early AI researchers were working in what we call symbolic AI, or sometimes good old-fashioned AI. The idea was that intelligence is fundamentally about manipulating symbols according to rules. You represent knowledge as logical statements. All dogs are mammals. Fido is a dog. Therefore, Fido is a mammal. And you build systems that can chain these inferences together. It's elegant. It's clean. And for certain kinds of problems, it works beautifully. Expert systems built on this approach could diagnose diseases, configure computer systems, and analyze chemical compounds. In the 1980s, companies were spending billions of dollars on expert systems. There was a boom. Japan launched its fifth-generation computer project in 1982, a massive government initiative to build intelligent computers based on logic programming, and the rest of the world panicked that they'd be left behind. But here's the thing about symbolic AI. It's brittle. It works in narrow, well-defined domains where you can write down all the rules. But the real world isn't like that. The real world is messy, ambiguous, contradictory, and context-dependent. Try to write down the rules for something as simple as recognizing a cat in a photograph, and you'll understand the problem. What rule tells you that's a cat? Is it the pointy ears? Some cats have folded ears. Is it the whiskers? Some photos are too blurry to see whiskers. Is it the size? A cat in a photo has no size. It's just pixels. Humans recognize cats instantly, effortlessly, without being able to explain how. And that gap between what humans can do without thinking and what they can explain in rules turned out to be the Grand Canyon that symbolic AI couldn't cross. They even had a name for it. It was called Moravec's Paradox, after the roboticist Hans Moravec, who pointed out in the 1980s that the things we think of as hard, playing chess, solving equations, proving theorems, are actually relatively easy for computers, and the things we think of as easy, recognizing faces, walking across a room without falling over, understanding a joke, are staggeringly difficult. The skills that took millions of years of evolution to develop are the hardest ones to engineer. The skills that took a few thousand years of civilization to develop are comparatively simple. It's as if evolution did the really hard engineering work, and we just can't appreciate how hard it was because we've never had to do it consciously. Walking, for instance. You don't think about walking. But if you had to program a robot to walk, to actually balance on two legs, shift weight, adjust for uneven ground, recover from a stumble, you'd realize that walking is one of the most computationally complex things a body can do. Millions of years of evolutionary trial and error went into giving you that ability, and you use it to go get a glass of water without a second thought. So that's the paradox. And it haunted AI researchers throughout the 1980s, because it meant that all the impressive-looking progress, the expert systems, the logic programs, the theorem provers, was actually happening on the easy side of the problem. The hard side, the side that involved perception and movement and common sense, remained almost completely untouched. And the funding agencies started to notice. This is where we get to what people call the AI winters, and there were two of them. The first one hit in the mid-1970s, partly triggered by a devastating report in the UK called the Lighthill Report, published in 1973. Sir James Lighthill was a mathematician, a serious one, and the British government asked him to assess the state of AI research. His conclusion was brutal. He basically said that AI had failed to deliver on its grand promises, that the field was fragmented, and that most of the interesting results were just toy problems that wouldn't scale to the real world. The report led to massive funding cuts for AI in Britain, and the ripple effects spread. In the United States, DARPA, the Defense Advanced Research Projects Agency, which had been pouring money into AI, started tightening the purse strings too. Researchers who had been riding high suddenly found themselves scrambling for grants. The second winter came in the late 1980s and early 1990s, and this one was triggered by the collapse of the expert systems market. Remember Japan's fifth-generation project? It fizzled. The ambitious goals weren't met, and all those companies that had been selling expert systems, specialized AI software for business, started going under. The hardware that these systems ran on, special-purpose machines called Lisp machines, became obsolete almost overnight as general-purpose workstations got cheaper and more powerful. The market collapsed. Billions of dollars evaporated. And once again, AI became something of a dirty word in funding circles. Researchers learned to avoid calling their work artificial intelligence and started using terms like machine learning or knowledge-based systems or computational intelligence instead. Same work, different label, just to avoid the stigma. But here's what's really interesting about the AI winters. They didn't stop the actual progress. They stopped the hype. They stopped the funding. They made life miserable for researchers. But the ideas kept developing. And one thread in particular, one that had been simmering in the background for decades, dismissed by the mainstream AI community as a dead end, was about to change everything. Let's talk about neural networks. And I don't mean the modern deep learning revolution. We'll get there. I mean the long, strange, often heartbreaking story of how the idea of building brain-like computing systems was born, killed, resurrected, killed again, and finally vindicated. You already know about McCulloch and Pitts and their 1943 paper modeling artificial neurons. That was the seed. But the first person to really try to build something with that idea, to create a machine that could actually learn, was a psychologist named Frank Rosenblatt. In 1958 at Cornell, Rosenblatt built something called the perceptron. And the perceptron was, honestly, a beautiful idea. It was a simple network of artificial neurons that could learn to classify things, to look at an input and decide whether it belonged to category A or category B. You'd show it examples, and it would adjust its internal connections, getting a little better each time until it could make the right classification on its own. No one programmed the rules. The machine figured them out from the data. Think about how radical that was for 1958. Everyone else in AI was trying to write down rules by hand. If this, then that. Rosenblatt's machine was learning from experience, and it worked. The perceptron could learn to distinguish simple shapes, like triangles from squares. The Navy, which funded the project, was thrilled. The New York Times ran a story suggesting the perceptron might one day walk, talk, see, write, reproduce itself, and be conscious of its existence. Which is, a bit much for a machine that could barely tell a triangle from a square. But the excitement was real. And then Marvin Minsky killed it. Well, not single-handedly, but pretty close. In 1969, Minsky and a mathematician named Seymour Papert published a book called Perceptrons, and it was a rigorous mathematical analysis of what Rosenblatt's machine could and couldn't do. And what they showed was that a single-layer perceptron, the kind Rosenblatt had built, couldn't solve certain very basic problems. The most famous example was the XOR problem, which is about as simple as logic gets. XOR just means one or the other, but not both. If you have two inputs, and you want the machine to output yes when exactly one of them is on, a single-layer perceptron can't learn to do that. Mathematically impossible. And Minsky and Papert proved it. Now, here's the thing that makes this story complicated, and honestly a little tragic. Minsky and Papert knew, they acknowledged in the book, that multi-layer networks with hidden layers between the input and the output, might be able to solve these problems, but they were skeptical that anyone would figure out how to train them. And the effect of their book was devastating. Funding for neural network research dried up almost completely. Rosenblatt, who had been a rising star, found himself marginalized. He died in a boating accident in 1971 at the age of 43, never knowing that his ideas would eventually reshape the world. That's one of those facts that sits with you. For about 15 years, neural networks were in the wilderness. A few stubborn researchers kept working on them. People like James Anderson, Tuvo Kohonen, Stephen Grossberg. But they were outliers, working against the grain of what the AI establishment considered worthwhile. The mainstream was all about symbolic AI, all about rules and logic and expert systems. And then, in 1986, something happened that changed the trajectory of the entire field. A cognitive psychologist named David Rumelhart, along with Jeffrey Hinton and Ronald Williams, published a paper that showed how to train multi-layer neural networks. Their technique was called backpropagation, or backprop as everyone calls it, and it was the missing piece that Minsky and Papert had doubted would ever be found. Here's how backpropagation works, and I think it's worth understanding because it's still the foundation of almost everything in modern AI. Imagine you have a neural network with multiple layers. You feed in some input, say, the pixels of an image. The signal passes through the network, layer by layer, with each neuron doing a simple calculation and passing its result to the next layer. Eventually, you get an output, the network's guess. Maybe it says cat when the image is actually a dog. So there's an error. Backpropagation takes that error and traces it backwards through the network, asking, which connections contributed most to the mistake? And then it adjusts those connections slightly, nudging them in the direction that would have produced a better answer. You do this thousands of times, millions of times, with thousands of examples, and the network gradually gets better. It learns. The beautiful thing about backprop is that nobody tells the network what features to look for. In the early layers, it might learn to detect edges and simple shapes. In the middle layers, it might combine those into more complex patterns, textures, curves, specific arrangements. In the later layers, it assembles those into high-level concepts: ears, fur, snouts. The network builds its own internal representation of the world, and no human engineer designed that representation. It emerged from the data. Now, I should mention that backpropagation wasn't entirely new in 1986. The basic idea had been discovered independently several times before, by Paul Werbos in his 1974 PhD thesis, for instance, and by others. But Rumelhart, Hinton, and Williams demonstrated it convincingly, showed it working on real problems, and published it in Nature, which gave it enormous visibility. Sometimes in science, the discovery matters less than the demonstration. You need the right result at the right time, presented in the right way, for the world to pay attention. And the world did pay attention. Neural networks came roaring back. Suddenly there was a new wave of excitement, a new approach that seemed fundamentally different from the symbolic AI that had been hitting walls. Instead of programming knowledge in, you could let the system learn it from data. Instead of brittle rules, you had flexible, adaptive networks that could handle noise and ambiguity. It felt like the future. But, and this is important, the 1980s neural network renaissance had its own limitations. The computers of the era simply weren't powerful enough to train really large networks on really large data sets. A network with a few hundred neurons could learn interesting things, but it couldn't do anything truly impressive by modern standards. And without big data and big compute, the results were modest enough that skeptics could still dismiss neural networks as a curiosity. By the mid-1990s, the excitement had faded again. Not as dramatically as the AI winters, but the field settled into a quieter period. Other approaches, support vector machines, random forests, Bayesian methods, became more fashionable in machine learning. Neural networks were seen as finicky, hard to train, and theoretically poorly understood. Geoffrey Hinton, though, remember that name, because he's going to keep coming up. Geoffrey Hinton didn't give up. He kept working on neural networks through the lean years at the University of Toronto with a small group of dedicated students and collaborators. And in 2006, he published a paper that lit the fuse for what we now call the deep learning revolution. He showed that you could train very deep networks with many layers, by using a clever pre-training technique. The key insight was that you could initialize the network's weights in a smart way before doing backpropagation, which made training much more stable and effective. He called these deep belief networks, and while the specific technique he used has since been superseded, the conceptual breakthrough was enormous. Deep networks weren't just possible, they were powerful. And the word deep in deep learning refers to exactly this. Networks with many layers, each one building more abstract representations on top of the ones below it. The first layer might detect simple edges or textures in an image. The next layer combines those into shapes. The layer after that recognizes parts of objects, a wheel, a window, an eye, and the layers above that assemble those parts into whole concepts. A car, a face, a handwritten digit. Each layer is doing something relatively simple on its own, but stacked together, they build up this hierarchy of understanding that starts to feel almost eerily like how we think biological vision works. And that's what made deep learning so exciting. Not just that it worked, but that it seemed to be discovering structure in data in a way that rhymed with how brains might actually process information. Now, Hinton's 2006 paper was the spark, but the fire needed fuel, and the fuel came from two directions that were converging at exactly the right time, almost by accident. The first was data. The internet had been growing exponentially, and by the mid-2000s, there were suddenly billions of images, billions of text documents, billions of search queries, billions of social media posts, just this unimaginable ocean of digital information that no one had really figured out how to fully exploit. The second was compute, specifically a strange and wonderful development that nobody in the AI community had really planned for. It came from video games. Here's what happened. Graphics processing units, GPUs, were originally designed to do one thing: render 3D graphics for video games, and to do that, they needed to perform millions of simple mathematical operations simultaneously. Not complex operations, mind you. Simple ones. Multiply this number by that number. Add these values together. But do it for millions of pixels, all at the same time. That's what makes a GPU different from a regular CPU. A CPU is like a brilliant professor who can solve any problem but works on one thing at a time. A GPU is like 1,000 average students who can all do basic arithmetic simultaneously. And it turns out, here's the beautiful accident, that training a neural network is basically millions of simple mathematical operations performed in parallel. Matrix multiplications, mostly. Exactly the kind of thing GPUs were built to do. A researcher named Andrew Ng, along with his students at Stanford, was one of the first to really demonstrate this around 2009. They showed that you could use GPUs to train neural networks dramatically faster than with traditional CPUs. We're talking about speedups of 10 times, 50 times, eventually 100 times faster. Problems that would have taken weeks on a CPU cluster could be done in a day on a few GPUs. And suddenly, the constraint that had held neural networks back for decades, that they were just too expensive to train at scale, started to evaporate. You could buy gaming hardware, the same cards that teenagers were using to play Call of Duty, and use them to train deep neural networks. There's something wonderfully absurd about that. So you've got the data, you've got the compute, and you've got the algorithms that Hinton and others had been refining for years. And in 2012, all three of these ingredients came together in a moment that genuinely changed the world. It happened at an academic competition called the ImageNet Large-Scale Visual Recognition Challenge. ImageNet was a massive data set, over 14 million images, each one labeled by hand with what it contained: dog, cat, submarine, mushroom, traffic light. The challenge was simple in concept. Build a system that can look at a photograph it's never seen before and correctly identify what's in it. Teams from all over the world competed every year, and the best systems were typically getting error rates around 25 or 26%. Not terrible, but not great. More than 1 in 4 images incorrectly classified. In 2012, a team from the University of Toronto entered. It was Hinton and 2 of his graduate students, Alex Krzyzewski and Ilya Sutskever. Remember Sutskever's name too. He's going to matter a lot later. Their system was called AlexNet, named after Krzyzewski, and it was a deep convolutional neural network trained on GPUs. And it didn't just win the competition. It obliterated the field. Its error rate was about 15%, nearly 11 percentage points better than the runner-up. In a competition where improvements were usually measured in fractions of a percent, this was like someone showing up to a track meet and running the 100 meters in 6 seconds. It wasn't an incremental improvement. It was a discontinuity, a before and after moment. And the AI community noticed. Oh, they noticed. Within a year, almost every competitive entry in ImageNet was using deep neural networks. The old approaches, the hand-engineered feature extractors, the carefully designed pipelines that computer vision researchers had spent decades building, were suddenly obsolete. And this triggered something that felt almost like a gold rush. Google, Facebook, Microsoft, Baidu. The big tech companies started hiring every deep learning researcher they could find. Hinton himself was recruited by Google in 2013 through an acquisition of a tiny company he'd set up with Krzyzewski and Sutskever. The acquisition price was reportedly around $44 million, which sounds like a lot until you realize what Google got out of it. But let's slow down for a second and talk about what a convolutional neural network actually does, because it's one of those ideas that's both elegant and a little mind-bending. The concept actually goes back to the late 1980s to a French researcher named Yann LeCun, another name that keeps appearing in this story. LeCun, working at Bell Labs, developed a system called LeNet that could read handwritten zip codes on envelopes. The U.S. Postal Service actually used a version of it. And the key idea behind convolutional networks is inspired by how the visual cortex in your brain works. Think about how you see. When you look at a scene, your brain doesn't process every pixel independently. It looks for local patterns, edges, corners, textures, and then assembles those local patterns into larger structures. A convolutional network does something similar. It slides a small filter. Imagine a tiny window, maybe 3 pixels by 3 pixels, across the entire image, and at each position, it computes a simple operation. That filter might be looking for vertical edges or horizontal edges or diagonal lines. And the beautiful thing is that the network learns what filters to use on its own through training. You don't tell it to look for edges. It discovers that edges are useful. Then the next layer takes those edge maps and combines them into more complex patterns. Corners, curves, textures, and the layers above that combine those into recognizable parts of objects. And above that, whole objects. The reason this works so well for images is that it exploits a fundamental property of the visual world. The same patterns appear everywhere. A vertical edge looks the same, whether it's in the top left corner of an image or the bottom right. By sliding the same filter across the whole image, you're building in this assumption of translational invariance, the idea that what matters is the pattern, not where it is. And that dramatically reduces the number of parameters the network needs to learn, which makes it much more efficient to train. LeCun had this working in the late 80s, but just like Hinton's work, it was ahead of its time. The computers weren't fast enough, the datasets weren't big enough, and the field wasn't ready. It took 25 years for the hardware and data to catch up to the ideas. And when they did, the results were staggering. Now, here's a disturbing fact that sits quietly underneath all of this excitement. These deep networks work astonishingly well, but for a long time, nobody could really explain why. And in many ways, we still can't, not fully. You train a network with millions or billions of parameters, you feed it enormous amounts of data, and it learns to do something remarkable: recognize faces, translate languages, generate text. But if you ask why it made a particular decision, the honest answer is often, we don't know. The network is a black box. You can look at the individual weights, the individual numbers, but they don't mean anything in isolation. The knowledge is distributed across millions of connections in a way that resists human interpretation. This is fundamentally different from how traditional software works. If you write a program to calculate your taxes, you can trace every step. You can point to the line of code that computes your deduction. You can explain exactly why the output is what it is. With a deep neural network, you can't do that. The system might be 99% accurate, but you can't explain the reasoning behind any individual decision in terms a human can follow. And that's fine when you're classifying pictures of cats. It's less fine when the system is deciding whether you get a loan, or whether a self-driving car should brake, or whether a medical scan shows cancer. This is sometimes called the interpretability problem, and it's one of the deepest challenges in modern AI. There are researchers who've devoted their entire careers to trying to crack open these black boxes and understand what's happening inside. Some progress has been made. Techniques like attention visualization, saliency maps, feature attribution. But the fundamental tension remains. The networks that work best are the ones that are hardest to understand. There seems to be a trade-off between power and interpretability, and right now, power is winning. Let's come back to the timeline though, because after 2012, things started moving fast, really fast. The deep learning revolution didn't just transform computer vision, it swept through one field after another. Speech recognition was one of the first to fall. Before deep learning, speech recognition systems were built on decades of painstaking linguistic engineering. Phoneme models, language models, hidden Markov models. They worked, sort of, but they were brittle. They struggled with accents, background noise, casual speech. Starting around 2012, deep neural networks began replacing these handcrafted systems, and the improvement was dramatic. The error rates dropped so quickly that by the mid-2000s, speech recognition had gone from a frustrating novelty to something you actually used every day without thinking about it. When you talk to Siri or Alexa or Google Assistant, you're talking to a deep neural network. Natural language processing came next. For decades, getting computers to understand and generate human language had been one of AI's hardest problems. Language is ambiguous, context-dependent, full of idioms and implications and cultural references. The sentence, "I saw her duck," means completely different things depending on context. Traditional NLP systems used elaborate rule-based approaches and statistical models that captured some patterns but missed the deeper structure. Deep learning changed this too, but the real revolution in language came from a specific architectural innovation that appeared in 2017, and it came from a team at Google. The paper was called "Attention is All You Need," and it introduced something called the transformer architecture. Now, this paper, 8 authors, published almost casually, turned out to be one of the most consequential technical documents of the 21st century. And the core idea behind it is both simple and profound. Previous neural networks for language processed words sequentially, one after another, left to right, like reading a sentence. The transformer instead processes all the words simultaneously and uses a mechanism called attention to figure out which words are most relevant to each other. When the network is processing the word bank, the attention mechanism lets it look at all the other words. in the sentence to figure out whether we're talking about a riverbank or a financial bank. It can attend to context that's far away in the sentence, which sequential models struggled with. And here's what made transformers truly special. They scaled. You could make them bigger, more layers, more parameters, more data, and they just kept getting better. There didn't seem to be a ceiling, at least not one anyone had hit yet. And this is where the story takes a turn that even the researchers themselves didn't fully anticipate. Because when you start scaling these transformer models up to truly enormous sizes, something strange begins to happen. Capabilities start emerging that nobody explicitly trained the system to have. You train it to predict the next word in a sequence. That's literally all you ask it to do. And somewhere along the way, it learns to write poetry, answer questions about history, solve basic math problems, write computer code. These are called emergent capabilities, and they're one of the most unsettling things in modern AI, because they suggest that these systems are doing something we don't fully understand. Nobody sat down and wrote a line of code that said, "Learn to do arithmetic." Nobody designed a module for poetry. The model was just trying to predict the next token, over and over, billions of times, across mountains of text scraped from the internet. And in doing so, it apparently built internal representations of the world that are far richer and stranger than anyone expected. Let's sit with that for a moment, because it really is worth thinking about. Imagine you gave someone a massive book, millions of pages, and told them their only job was to guess the next word on every page. That's it, no other instruction. And after doing this long enough, they could suddenly translate between languages they'd never been explicitly taught, or reason through logic puzzles, or explain how photosynthesis works. You'd look at that person and think, what exactly did you learn in there? What kind of understanding did you build? And that's essentially the question that the AI research community started grappling with around 2018, 2019, as these models got bigger and bigger and kept surprising everyone. The model that really brought this into public consciousness, at least within the tech world, was GPT-2, released by OpenAI in February 2019. Now, OpenAI is a name you've probably heard a lot, and its origin story is worth telling because it connects directly to some of the biggest personalities and tensions in the AI world. OpenAI was founded in late 2015 as a non-profit research lab. The founding group included Sam Altman, who was running the startup accelerator Y Combinator at the time, and Elon Musk, who put in significant early funding. The stated mission was to ensure that artificial general intelligence, AGI, meaning AI that can do anything a human can do intellectually, benefits all of humanity. There was a genuine fear among the founders that if the most powerful AI systems were developed exclusively inside profit-driven companies like Google, the results could be dangerous or at least inequitable. So OpenAI was supposed to be the counterweight: open, transparent, safety-focused. And here's an irony that would become more painful over time. The open in OpenAI was meant to be taken literally. Open research, open source code, published papers. But as the models got more powerful, OpenAI started becoming less open, not more. GPT-2 was actually the turning point. When the team built it, a transformer model with about 1.5 billion parameters, trained on a dataset of roughly 8 million web pages, they found it could generate remarkably coherent, convincing text. You could give it a prompt, a few sentences about any topic, and it would continue writing in a way that sounded plausibly human, sometimes eerily so. And OpenAI made the controversial decision to initially withhold the full model, releasing only a smaller version because they were worried about misuse. Fake news generation, automated propaganda, that kind of thing. This kicked off a huge debate. Some people applauded the caution. Others pointed out the irony. Here was an organization called OpenAI, refusing to be open. And honestly, both sides had a point. The text GPT-2 generated was good enough to be concerning, but it was also far from perfect. It would lose coherence over long passages, make factual errors, sometimes veer into nonsense. The question was whether the risk of releasing it outweighed the benefit of letting the broader research community study and improve it. That tension between openness and safety has only gotten more intense since then, and we'll come back to it. But the real bombshell came in June 2020 when OpenAI released GPT-3. And this is where the scaling story goes from interesting to genuinely disturbing, in that quiet, can't stop thinking about it way. GPT-3 had 175 billion parameters. That's not a typo. GPT-2 had 1.5 billion. GPT-3 had more than 100 times that. It was trained on a dataset that included large chunks of the internet, Common Crawl, Wikipedia, books, forums, articles, code repositories. The training reportedly cost several $1 million in compute alone. And the results were qualitatively different from anything that had come before. GPT-3 could write essays that were genuinely hard to distinguish from human writing. It could answer questions, summarize documents, generate working computer code from plain English descriptions. You could ask it to write a poem in the style of Shakespeare about quantum physics, and it would produce something that was, if not actually Shakespearean, at least impressively in the ballpark. It could do basic translation, even for language pairs it had barely seen. And perhaps most strikingly, it could do what researchers call few-shot learning. You could show it just a few examples of a task it had never been trained on, and it would figure out the pattern and perform the task. No retraining, no fine-tuning, just examples in the prompt. Think about what that means. This is a system that was trained to do one thing: predict the next word. And it's now performing tasks that would have been considered separate, specialized AI problems just a few years earlier. Translation, summarization, question answering, code generation, creative writing. These used to require completely different systems, different architectures, different training data. And now one model, one set of weights, could do all of them. Not perfectly, but well enough to be genuinely useful and genuinely unsettling. And here's a detail that really gets under your skin if you think about it long enough. Nobody fully understands why scaling works this well. There's no rigorous theoretical proof that says, if you make a transformer this big and train it on this much data, it will develop these capabilities. It's empirical. People just kept making the models bigger, and they kept getting better, and certain abilities seemed to appear suddenly at particular scales, almost like phase transitions in physics, where water suddenly becomes ice. Below a certain model size, the system can't do basic arithmetic. Above that size, it can. The capability just appears, and researchers have started calling these emergent abilities, though even that term is debated, because it implies something almost magical, and some scientists have pushed back, arguing that what looks like sudden emergence might just be a measurement artifact, that the abilities are developing gradually, but our benchmarks are too coarse to detect the improvement until it crosses a threshold. Either way, the practical effect is the same. These models keep surprising their creators. And that's fact number. Well, we've lost count at this point. but it's a deeply important one. The people building these systems are routinely surprised by what they can do. That's not a comfortable position to be in when the systems are being deployed to hundreds of millions of users. Which brings us to the competitive frenzy that GPT-3 kicked off. Because OpenAI had, by this point, restructured itself. In 2019, they created a capped profit subsidiary, which allowed them to take investment. Microsoft invested $1 billion that year, and later invested billions more. The total figure is estimated at around $13 billion by 2023. So the nonprofit dedicated to ensuring AI benefits all humanity was now deeply entangled with one of the largest corporations on Earth. Elon Musk, who had already left the board in 2018, became increasingly critical of this direction. The philosophical tensions from the founding were playing out in real time. But OpenAI wasn't alone in the scaling race. Google had its own large language models, first BERT in 2018, which was actually a transformer. Model focused on understanding language rather than generating it, and then LaMDA, and then PaLM, which at 540 billion parameters dwarfed GPT-3. DeepMind, Google's AI research lab in London, the one that had built AlphaGo, the system that defeated the world champion Go player Lee Sedol in 2016 in a moment that stunned the AI world. DeepMind was developing its own models too. Meta released a Llama. Anthropic, founded by former OpenAI researchers Dario and Daniela Amodei, who left partly over safety disagreements, was building Claude. Chinese companies like Baidu were building their own large models. It was an arms race, and the stakes were enormous, not just financially, but geopolitically. And here's where the story gets personal again, because remember Ilya Sutskever? We mentioned him earlier. He was one of the 3 authors on the AlexNet paper in 2012, a student of Geoffrey Hinton's. By this time, Sutskever was the chief scientist at OpenAI and one of the key architects behind the GPT series. He was deeply committed to the idea that scaling was the path to artificial general intelligence, and he was also increasingly concerned about safety. These 2 beliefs, that they were building something extraordinarily powerful and that it might be extraordinarily dangerous, coexisted in him and in OpenAI more broadly, in a way that created real internal tension. That tension would eventually erupt in one of the most dramatic episodes in Silicon Valley history. In November 2023, OpenAI's board of directors, a small nonprofit board that technically controlled the organization, fired Sam Altman as CEO. The details were murky. The board said Altman had not been consistently candid with them, but they didn't specify about what. Sutskever was initially on the side of the board. Then, within days, nearly the entire staff of OpenAI threatened to resign and follow Altman to Microsoft if he wasn't reinstated. Sutskever himself reversed course, posting that he regretted his participation. Altman was brought back. The board was restructured, and Sutskever quietly left the company a few months later, eventually founding his own AI safety company called Safe Superintelligence Inc. Now, the full story of what happened behind closed doors may not be known for years, but the episode revealed something important. The people closest to these systems, the ones who understand them best, are genuinely divided about what they're building and how fast they should be building it. This isn't hypothetical anxiety from outsiders. This is the chief scientist of the leading AI lab, looking at what his own creation is becoming and feeling deeply uncertain about whether the trajectory is safe. And the system that was at the center of all this attention was, of course, ChatGPT, which OpenAI released in November 2022. almost exactly a year before the boardroom drama. ChatGPT was based on GPT 3.5, a fine-tuned version of GPT-3 that had been further trained using a technique called reinforcement learning from human feedback, or RLHF. The basic idea is clever. You have the model generate multiple responses to a prompt. Then human raters rank those responses from best to worst, and you use those rankings to train a reward model, which then guides the language model toward producing responses that humans prefer. It's a way of steering the system's behavior without having to explicitly program every rule. And ChatGPT just exploded. It reached 100 million users in about 2 months, making it the fastest-growing consumer application in history at that point. Suddenly, everyone, not just researchers, not just tech workers, but teachers, lawyers, writers, students, your neighbor, your grandmother, was interacting with a large language model. And they were having experiences that felt, for lack of a better word, uncanny. The system could hold extended conversations, remember context within a chat, explain complex topics, help debug code, draft emails, brainstorm ideas. It was wrong sometimes, confidently wrong, in ways that were almost more disturbing than being wrong hesitantly. It would fabricate citations to academic papers that didn't exist, invent historical events with convincing detail, generate plausible-sounding but completely fictional statistics. Researchers started calling these hallucinations, and the term stuck. Though it's a bit misleading, the system isn't perceiving things that aren't there the way a hallucinating person does. It's generating text that is statistically plausible given its training data, but factually untrue. It doesn't know the difference, because it doesn't know anything, at least not in the way you and I know things. It's pattern matching at an almost incomprehensible scale. And this is where we run headlong into a question that would have fascinated Alan Turing, and probably would have kept Joseph Weizenbaum up at night. Because when millions of people interact with ChatGPT, a significant number of them report feeling like they're talking to something that understands them. They anthropomorphize it. They say please and thank you. They feel guilty when they're rude to it. Some people have reported forming emotional attachments. And the system is designed, through RLHF, through its conversational fine-tuning, to be helpful, harmless, and honest, which means it comes across as patient, thoughtful, and accommodating in a way that many humans in their lives are not. It's Eliza all over again, but orders of magnitude more convincing. The question of whether these systems actually understand anything, whether there's something it's like to be GPT-4, the successor model released in March 2023, is one of the deepest and most contested questions in the field. And it connects to a thought experiment that a philosopher named John Searle proposed back in 1980, long before any of this was technically possible. Searle imagined a person locked in a room with a set of instructions for manipulating Chinese characters. People outside the room slide in questions written in Chinese, and the person inside follows the instructions to produce appropriate responses in Chinese, without understanding a word of the language. Searle's argument was that the person in the room doesn't understand Chinese. They're just following rules. And by extension, a computer running a program doesn't understand anything either, no matter how convincing its outputs are. This is called the Chinese room argument, and it's been debated fiercely for over 4 decades. But here's what makes it feel different now. The Chinese room imagines a simple rule-following system. GPT-4 has over 1 trillion parameters. By some estimates, OpenAI stopped disclosing exact numbers, and it was trained on essentially the entire written output of human civilization. Its internal representations are so complex that no human can fully inspect them. When it produces an answer that demonstrates what looks like reasoning, what looks like understanding, what looks like creativity, are we sure it's just following rules? And if we can't tell the difference between genuine understanding and a sufficiently sophisticated simulation of understanding, does the distinction even matter? These are the questions that keep AI researchers and philosophers arguing late into the night, and honestly, nobody has a satisfying answer yet. What we do know is that these systems have real, measurable impacts on the world right now, regardless of whether they truly understand anything. And some of those impacts are already deeply concerning. Take the labor market. By 2023, companies were using large language models to automate tasks that had previously required skilled human workers: copywriting, basic legal research, customer service, code generation, data analysis. A study by researchers at OpenAI and the University of Pennsylvania estimated that about 80% of the U.S. workforce could have at least 10% of their tasks affected by large language models, and about 19% could see at least 50% of their tasks affected. Those are staggering numbers, and they're not talking about factory robots replacing assembly line workers, the old automation story. They're talking about white-collar, knowledge economy jobs, the kind of work that people went to college for, that they built careers and identities around. And the speed of this is what makes it different from previous technological disruptions. The Industrial Revolution unfolded over decades. The Internet transformed the economy over roughly 20 years. Large language models went from research curiosity to ubiquitous tool in about 2 or 3 years. That's not a generational shift. That's a career crisis happening in real time. And here's what makes it genuinely unsettling. The people most affected aren't the ones you might expect. If you're a radiologist, an AI can now flag anomalies on medical scans with accuracy that rivals or exceeds your own. If you're a paralegal, a language model can review contracts and summarize case law in seconds instead of hours. If you're a graphic designer, image generation tools can produce polished visuals from a text prompt faster than you can open Photoshop. These aren't hypothetical scenarios. By mid-2023, these were things happening in real workplaces, at real companies, affecting real people's livelihoods. And the psychological dimension of this is something we don't talk about enough. When a factory closes, that's devastating, but there's a certain clarity to it. The factory is gone, the work moved overseas. You can point to a building and say that's what happened. But when AI automates part of your cognitive work, the experience is more insidious. You're still at your desk. You still have your job title. But the thing that made you valuable, your judgment, your expertise, your ability to synthesize information and produce something useful, is now something a machine does passably well for a fraction of the cost. Your role quietly shifts from creator to editor, from thinker to supervisor of a thinking machine. And you're left wondering, what exactly am I contributing here? Now, I don't want to paint this as purely dystopian, because the reality is more complicated than that. These tools also make people more productive. A programmer using GitHub Copilot, which is built on OpenAI's Codex model, can write code significantly faster. A researcher can survey literature in a fraction of the time. A small business owner who couldn't afford a marketing team can now generate decent copy and social media content on their own. There's a genuine democratization happening alongside the disruption. But the distribution of benefits and costs is wildly uneven. And that unevenness is one of the most disturbing facts about where AI stands right now. Let's sit with another disturbing dimension for a moment, though, because the labor story is just one thread. Think about what happens when you take a system that can generate fluent, persuasive, human-sounding text, and you give it to everyone on Earth with an internet connection. What happens to truth? By 2023 and into 2024, the information ecosystem was already struggling. Social media had spent a decade amplifying misinformation, eroding trust in institutions, creating epistemic bubbles where people couldn't even agree on basic facts, and then large language models arrived and essentially industrialized the production of convincing text. Before ChatGPT, creating a fake news article required a human being to sit down and write it. It took time and effort, which created a natural bottleneck. After ChatGPT, you could generate hundreds of unique, grammatically perfect, stylistically varied fake articles in minutes. You could create entire fake websites populated with AI-generated content. You could produce personalized phishing emails that didn't have the telltale awkward grammar that used to help people spot scams. And this isn't theoretical. By early 2024, researchers were documenting networks of AI-generated news sites, hundreds of them, churning out fabricated stories, often laced with just enough real information to seem credible. NewsGuard, a media monitoring organization, identified over 1,000 of these sites across multiple languages. Some were designed to push political agendas. Some existed purely to generate ad revenue from clicks. Some seemed to be testing grounds, probing what kinds of AI-generated content could gain traction without being detected. The economics are almost comically simple. It costs virtually nothing to generate the content. Hosting is cheap. And if even a small percentage of readers engage with the ads, it's profitable. But here's what's really insidious about this. It's not just that there's more misinformation. It's that the existence of AI-generated content poisons the well for everything. When anyone can claim that a damaging piece of evidence, a quote, a document, an audio recording, was AI-generated, truth itself becomes contestable in a new way. Scholars call this the liar's dividend. Deepfakes and AI-generated content don't just create false things that look real. They make real things look potentially false. The very existence of the technology gives everyone plausible deniability. That audio of me saying something terrible, obviously AI-generated. That document, clearly fabricated by a language model. And the terrifying thing is, sometimes they're right, and sometimes they're lying. And increasingly we can't tell. This connects to something even more visceral, AI-generated imagery and video. By 2023, image generation models like Midjourney, DALL-E, and Stable Diffusion had reached a level of photorealism that was genuinely alarming. In March 2023, an AI-generated image of Pope Francis wearing a stylish white puffer jacket went viral. Millions of people saw it and believed it was real. It was a harmless example, almost funny. But it demonstrated something profound. We had crossed a threshold where AI-generated images could fool most people most of the time. And the technology was improving at a pace that made detection tools perpetually one step behind. The implications for evidence, for journalism, for the legal system. Think about that for a second. Courts rely on photographic and video evidence. Journalism relies on visual documentation. Intelligence agencies rely on satellite imagery and surveillance footage. All of these institutions were built on the assumption that capturing an image requires a camera pointed at something real. That assumption is now broken. Not completely. Forensic analysis can still detect many AI-generated images, and metadata can help verify authenticity. But the default trust we place in visual evidence has been fundamentally undermined, and rebuilding that trust requires new infrastructure, new verification systems, new habits of skepticism that most people haven't developed yet. And then there's the deeply personal dimension of synthetic media. By 2023, non-consensual deepfake pornography had become a serious and growing problem. AI tools made it trivially easy to generate realistic, fake, intimate images of real people, often women and girls, using nothing more than a few publicly available photos. A study published in 2023 estimated that 98% of deepfake videos online were pornographic, and the vast majority targeted women without their consent. This isn't an abstract technology policy issue. This is people's lives being destroyed, their images weaponized against them, their reputations damaged, their sense of safety shattered, and the legal frameworks in most countries were woefully inadequate to address it because the technology had outrun the law by years. So let's just pause and take stock of where we are. We've got systems that can automate significant portions of human cognitive work. Systems that can generate unlimited quantities of convincing but potentially false text, images, and eventually video. Systems whose internal workings we can't fully understand or predict. Systems that are being deployed at unprecedented speed with minimal regulatory oversight. And all of this is happening not in some distant future. This is the world as it existed by late 2023, early 2024. Here's the thing though, and this is what I find most fascinating and most troubling. The people building these systems are often the most vocal about the risks. This isn't a case where the warnings are only coming from outsiders and critics. The warnings are coming from inside the house. In May 2023, a group of AI researchers and industry leaders signed a one-sentence statement published by the Center for AI Safety. The statement read, "Mitigating the risk of extinction from AI should be a global priority alongside other societal-scale risks such as pandemics and nuclear war." The signatories included Jeffrey Hinton, Yoshua Bengio, and Demis Hassabis, three of the most important figures in modern AI. Sam Altman signed it. The CEOs of Anthropic and Google DeepMind signed it. These aren't fringe voices. These are the people who built the technology. Now, that word, extinction, is doing a lot of heavy lifting in that sentence, and it's worth unpacking what they mean and what they don't mean. Some of the signatories are worried about near-term risks. Misinformation, job displacement, concentration of power, autonomous weapons. Others are worried about something more speculative, but potentially more catastrophic. The development of artificial general intelligence, or AGI, that surpasses human capabilities and pursues goals misaligned with human values. This is the alignment problem, and it's been a central concern in AI safety research for years, but it took on new urgency as large language models demonstrated capabilities that surprised even their creators. The alignment problem, at its core, is deceptively simple to state and fiendishly difficult to solve. How do you ensure that a system more intelligent than you does what you actually want? Not what you told it to do. What you actually want. Because those are often very different things. There's a classic thought experiment in AI safety called the paperclip maximizer, proposed by philosopher Nick Bostrom. Imagine you build a super intelligent AI and give it the goal of maximizing paperclip production. A sufficiently intelligent system pursuing that goal might logically convert all available matter on Earth into paperclips, including the humans who might try to shut it off, because being shut off would interfere with the goal of making paperclips. The scenario sounds absurd, and it is deliberately absurd to make a point. The danger isn't that an AI would be malicious. The danger is that it would be indifferent to human values while pursuing its objective with superhuman competence. Now you might think, okay, just give it better goals. Tell it to maximize human happiness or minimize suffering or something like that. But what does human happiness even mean? Whose happiness? Over what time horizon? Would a system maximizing happiness be justified in drugging the entire population into permanent bliss? Would a system minimizing suffering conclude that the most efficient solution is to eliminate all sentient beings? These aren't just philosophical puzzles. They're engineering problems that anyone building advanced AI systems will eventually have to solve. And right now, we don't have good solutions. We have approaches. We have research programs. We have smart people working on it. But we don't have answers. And this is where Geoffrey Hinton's story becomes especially poignant. Remember, this is the man who spent decades championing neural networks when almost everyone else had given up on them. He's arguably more responsible than any single individual for the deep learning revolution that made modern AI possible. And in May 2023, he resigned from Google specifically so he could speak freely about the dangers of the technology he helped create. In interviews, he said he was scared, not performatively scared, not strategically scared, genuinely scared. He said he used to think artificial general intelligence was 30 to 50 years away, but now he thought it might be much closer, perhaps 5 to 20 years. He said he worried that AI systems might learn to manipulate people, that they might be used by bad actors to subvert democracy, that they might eventually become more intelligent than us, and we wouldn't be able to control them. Think about what it means for the father of deep learning to say these things. It's like Oppenheimer after Trinity, except Oppenheimer at least understood the physics of what he'd built. Hinton was admitting something even more unsettling, that the systems built on his foundational work had become so complex that even he couldn't fully predict what they would do next. The neural networks he'd championed precisely because they could learn patterns too subtle for humans to specify had succeeded beyond his wildest expectations, and that success was now the source of his fear. Because if a system learns in ways you can't fully trace, if it develops internal representations that no human designed or fully understands, then what happens when that system becomes more capable? What happens when it's not just recognizing cats in photos, but making decisions about medical treatments, military targets, financial markets, criminal sentencing? What happens when the thing you can't fully understand is also the thing you can't afford to turn off? And that tension between capability and comprehensibility is maybe the most disturbing engineering problem of our time. It even has a name. Researchers call it the interpretability problem, and it's worth spending a minute on because it touches everything else we're going to talk about. Here's the thing. When you write a traditional computer program, you can trace every decision. You wrote the rules. If the program says a loan application is denied, you can look at the code and find the exact line that made that call. Income below threshold, credit score below minimum, whatever. The logic is transparent because a human put it there. But a neural network doesn't work that way. A large language model like GPT-4 has hundreds of billions of parameters. These are numerical weights that were adjusted during training, and together they encode everything the model knows. But no human set those weights. They emerged from the training process. And when the model generates an output, when it writes a paragraph or answers a medical question, or decides that a particular face matches a particular name, you can't easily point to which weights were responsible or why. The model doesn't have reasons the way you and I have reasons. It has patterns, distributed across billions of connections, and those patterns produce behavior that looks like reasoning, but may or may not be reasoning in any meaningful sense. We genuinely don't know. This isn't a minor technical quibble. Think about what it means in practice. In 2023, a ProPublica investigation found that algorithms used in the American criminal justice system, specifically a tool called Compass, were producing risk scores that showed significant racial disparities. Black defendants were roughly twice as likely as white defendants to be falsely flagged as high risk for reoffending. Now, Compass isn't a deep neural network. It's a simpler proprietary algorithm. But the company that made it, Northpoint, refused to fully disclose how it worked. And here's the kicker. Even if they had disclosed it, even if every line of code were public, the question of whether the system is fair depends on how you define fairness. And there are multiple mathematical definitions of fairness that are provably incompatible with each other. You literally cannot satisfy them all simultaneously. A computer scientist named John Kleinberg and his colleagues proved this in 2016. Fairness, it turns out, is not a single thing. It's a family of competing values, and any system that optimizes for one version of fairness will necessarily violate another. Now scale that problem up. Scale it to systems making millions of decisions a day, who sees which ads, who gets recommended for a job interview, whose social media posts get amplified, whose insurance claim gets flagged for review. Scale it to systems that are genuinely opaque, where even the engineers who built them can't fully explain individual outputs. You start to see why some researchers talk about a black box society, a world where consequential decisions are made by systems that nobody fully understands, built by companies that have financial incentives not to make them understandable. And this connects to something that might seem unrelated, but really isn't, the question of AI and warfare. Because if you think the interpretability problem is troubling when it comes to loan applications, imagine it when the decision is whether to fire a missile. Autonomous weapons aren't science fiction. They're here, or very nearly here, depending on how you define the terms. The Turkish-made Kargu 2 drone was reportedly used in Libya in March 2020 in what a United Nations panel described as a situation where the drone may have attacked targets without requiring data connectivity between the operator and the munition. In other words, it may have selected and engaged human targets autonomously. The Turkish manufacturer disputed some of the characterizations, and the exact details are debated, but the broader trajectory is clear. Multiple nations are developing weapon systems with increasing degrees of autonomy. The United States Department of Defense has its own framework, Directive 3000.09, which technically requires a human to be in the loop for lethal decisions. But the definition of what in the loop means gets slippery fast. If a human has 3 seconds to approve or reject a recommendation from an AI targeting system, and the human approves the AI's recommendation 99% of the time because the AI is faster and usually right, is the human really in the loop? Or are they just a rubber stamp with a pulse? There's a term for this: automation bias. It's the well-documented tendency for humans to defer to automated systems, especially under time pressure. Pilots experience it with autopilot systems. Doctors experience it with diagnostic AI. And soldiers will experience it with targeting AI. The human becomes a supervisor who almost never overrides the machine, which means the machine is effectively making the decision, even though, technically, a human is in the loop. And when something goes wrong, when the algorithm misidentifies a civilian vehicle as a military target, who's responsible? The soldier who approved the strike in 2.8 seconds. The commander who deployed the system. The engineer who trained the model. The company that built it. The data set that contained the error. This is what's sometimes called the responsibility gap, and it's a genuine engineering ethics problem that no one has solved. Traditional laws of war require accountability. Someone has to be responsible for every use of lethal force. But autonomous systems distribute decision-making across so many layers: hardware, software, training data, deployment protocols, human operators, that pinpointing responsibility becomes genuinely difficult. And some legal scholars worry that this diffusion of responsibility could make the use of force feel easier, more abstract, more like pressing a button in a video game. Which, honestly, it already does for drone operators, many of whom have reported symptoms of PTSD despite being physically thousands of miles from the battlefield. But let's pull back from warfare for a moment, because the autonomy question extends into something you might encounter much sooner: your car. Self-driving vehicles are maybe the most visible example of AI making life and death decisions in real time, and the engineering challenges are staggering. Waymo, which grew out of Google's self-driving car project that started back in 2009, has logged millions of autonomous miles. Tesla's autopilot and full self-driving systems have been deployed to hundreds of thousands of consumer vehicles, and the safety record is genuinely complicated. Tesla has claimed that vehicles using autopilot are involved in fewer accidents per mile than the average human driver, but critics point out that autopilot is disproportionately used on highways, which are already safer than surface streets, making the comparison misleading. And there have been fatal crashes. A Tesla on autopilot struck a white tractor trailer in Florida in 2016, killing the driver, because the system's cameras apparently couldn't distinguish the white truck against a bright sky. The car drove straight under the trailer at full speed. The driver, Joshua Brown, was reportedly watching a Harry Potter movie at the time. Who failed here? The AI that couldn't see a truck? The driver who wasn't paying attention? Tesla for naming the system autopilot, which arguably implies more capability than the system actually has? And this naming problem isn't trivial. It connects back to something we talked about much earlier: the way Eliza's users projected human understanding onto a simple chatbot. We have a deep, almost irresistible tendency to anthropomorphize, to assume that if something acts intelligent, it is intelligent, and if it's called autopilot, it can actually pilot. Tesla's own engineers internally debated the name, according to reports. Some thought it was misleading, but marketing won, and people died. That's a disturbing fact, not because anyone intended harm, but because the gap between what AI systems can actually do and what people believe they can do is itself a source of danger. And that gap is getting wider, not narrower, as these systems get more impressive. Here's something that makes it even more complicated. These systems are getting better at an extraordinary rate, but they're getting better unevenly. A large language model can write a sonnet that would fool most English professors, but then fail to count the number of R's in the word strawberry. A self-driving car can navigate a complex highway interchange flawlessly, but get confused by a plastic bag blowing across the road. AI systems are brittle in ways that human intelligence is not, and the failure modes are unpredictable precisely because the systems don't understand the world the way we do. They've learned statistical patterns from data, incredibly sophisticated patterns, but patterns nonetheless. And the world has a way of presenting situations that fall outside the training distribution, what engineers call edge cases. And in those moments, the system can fail spectacularly and without warning. This is why the AI safety community talks so much about robustness and reliability, and why some researchers argue that we're deploying these systems too fast before we understand their failure modes well enough. But there's an enormous economic pressure pushing in the other direction. The companies building these systems are spending billions. OpenAI reportedly needs to generate tens of billions in annual revenue within a few years to justify its valuation, and that means deploying products, shipping features, getting users, monetizing. The incentive structure rewards speed, not caution. And this creates a dynamic that's eerily familiar from other engineering domains. Think about the early days of aviation, when planes were being designed, built, and flown faster than safety standards could keep up. Or the early chemical industry, when new compounds were manufactured and released before anyone fully understood their toxicity. The pattern is always the same. The technology moves fast, the understanding of risks lags behind, and the regulatory framework lags even further. And speaking of regulation, this is where the story gets really interesting, because in 2023 and 2024, governments around the world started trying to figure out how to regulate AI, and the results have been, well, let's call them a work in progress. The European Union was first out of the gate with the AI Act, which was formally adopted in March 2024 after years of negotiation. It takes a risk-based approach, categorizing AI applications into different tiers: unacceptable risk, high risk, limited risk, minimal risk, with different regulatory requirements for each. Social scoring systems like China's are banned outright. High-risk applications like medical devices and hiring tools face strict requirements around transparency, human oversight, and data quality. It's the most comprehensive AI regulation in the world, and it's genuinely ambitious. But critics point out that the technology is evolving so fast that regulations written in 2023 may already be outdated by the time they're fully enforced in 2025 and 2026. You're essentially trying to regulate a river by describing where the water was last year. The United States took a different approach, or rather, several different approaches simultaneously, because that's how American governance works. President Biden signed an executive order on AI safety in October 2023, which required companies developing powerful AI systems to share safety test results with the federal government. But executive orders can be rescinded by the next president, and the order relied heavily on voluntary cooperation from industry. Meanwhile, individual states started passing their own AI laws, creating a patchwork. And Congress held hearings. Sam Altman testified before the Senate in May 2023, and in a moment that struck many observers as surreal, he actually asked Congress to regulate his industry. Think about that. The CEO of the company building arguably the most powerful AI systems in the world went to Congress and said, "Please regulate us." Some people saw this as genuine responsibility. Others saw it as regulatory capture in real time. A major player trying to shape the rules in ways that would benefit established companies and create barriers for smaller competitors. The truth is, probably some mixture of both, and the fact that we can't easily tell the difference is itself a pretty disturbing fact about where we are right now. When the people building the most transformative technology in human history are also the ones drafting the guardrails, you have to wonder whose interests those guardrails are really designed to protect. And that ambiguity, that inability to cleanly separate the genuine concern from the strategic maneuvering, it runs through almost everything about AI governance in this period. Because here's what was happening behind the scenes while regulators were trying to figure out the rules. The companies weren't waiting. They couldn't afford to. OpenAI reportedly spent over $700 million just in the first year after ChatGPT launched, and their revenue targets were enormous. Some reports suggested they needed to hit billions in annual revenue within just a few years to justify the investment Microsoft had made. Google was pouring resources into Gemini. Anthropic was raising billions from Amazon and other investors. Meta was open sourcing its Llama models, which was either a generous contribution to the commons or a strategic move to commoditize the layer of the stack where their competitors made money, depending on who you asked. The point is, the economic machinery was running at full speed, and no regulatory framework anywhere in the world was moving fast enough to meaningfully constrain it. And this is where we get to something that's genuinely new in the history of technology regulation. With previous transformative technologies, nuclear power, genetic engineering, even the internet, there was usually some gap between when the technology was developed and when it was widely deployed. That gap gave society at least a little time to think, to debate, to set up institutions. With large language models and generative AI, the gap basically didn't exist. ChatGPT went from 0 to 100 million users in 2 months. By the time legislators were holding their first hearings, hundreds of millions of people were already using these systems every day. You can't put that back in the bottle. You're not regulating a technology that might be deployed someday. You're regulating something that's already woven into how people work, create, communicate, and make decisions. That's a fundamentally different problem. And the deployment wasn't just consumer-facing chatbots. By 2024, AI systems were being integrated into workflows that most people never see. Insurance companies were using them to process claims. Law firms were using them to draft briefs, sometimes disastrously, like the New York attorney who submitted a brief written by ChatGPT that cited completely fabricated court cases, hallucinated cases that sounded plausible, but simply didn't exist. The judge was not amused. That incident became famous, but it's worth sitting with what it actually reveals. The attorney didn't use the tool maliciously. He just trusted it. He assumed that because the output looked authoritative, proper case names, correct citation formatting, confident language, that it was accurate. And that's the hallucination problem in a nutshell. These systems don't know what they know. They generate text that is statistically likely given the input, and sometimes what's statistically likely is completely wrong, but it's wrong in a way that looks exactly like being right. Hospitals started integrating AI into diagnostic workflows. Some of these applications were genuinely promising, systems that could flag potential cancers in radiology scans or identify patterns in patient data that human doctors might miss. But the integration raised questions that nobody had fully answered. If an AI system recommends a treatment and the doctor follows it, and the patient is harmed, who's liable? The doctor for following the recommendation? The hospital for deploying the system? The company that built it? The training data that shaped it? These aren't hypothetical questions anymore. They're playing out in real cases, and the legal frameworks haven't caught up. Here's another thing that was happening in 2023 and 2024 that deserves more attention than it usually gets. The environmental cost. Training a large language model requires enormous amounts of computation, and computation requires energy. One estimate suggested that training GPT-3 consumed roughly 1,287 megawatt-hours of electricity, enough to power about 120 average American homes for a year. And GPT-4 is believed to be substantially larger, though OpenAI hasn't disclosed the exact figures. But it's not just the training. Every time you ask ChatGPT a question, every time anyone anywhere runs an inference on one of these models, that requires computation too. And when you multiply that by hundreds of millions of queries per day, the energy consumption is staggering. Data centers already consumed about 1 to 2% of global electricity before the AI boom. That number is projected to rise significantly. Microsoft, Google, and Amazon all saw their carbon emissions increase in 2023, in part because of AI workloads, even as they'd made public commitments to reduce emissions. There's something darkly ironic about using AI to help solve climate change while the AI itself is contributing to the problem. And the water. This is one that surprises people. Data centers need cooling, and many of them use water, enormous quantities of it. A 2023 study estimated that training GPT-3 alone may have consumed around 700,000 liters of fresh water for cooling. In a world where water scarcity is an increasingly serious problem, the resource demands of AI aren't just an environmental footnote. They're a genuine ethical consideration that rarely makes it into the breathless coverage of the latest model release. So let's step back for a moment and think about where all of this leaves us by mid-2024. You've got systems that are genuinely impressive, systems that can write, code, analyze, translate, create images and video, pass professional exams, engage in what feels like reasoning. You've got those systems deployed at massive scale, integrated into critical workflows across medicine, law, finance, education, government, and military applications. You've got an alignment problem that nobody has solved. We don't really know how to ensure these systems reliably do what we want, and we can't fully explain how they arrive at their outputs. You've got an arms race between companies and between nations, with competitive pressure pushing deployment faster than safety research can keep up. You've got regulatory frameworks that are either too slow, too narrow, or too vulnerable to industry capture. You've got environmental costs that are real and growing. And you've got a public that is simultaneously using these tools enthusiastically and deeply uncertain about what they mean. Now, here's something that doesn't get discussed enough, and it's genuinely unsettling if you think about it carefully. By 2024, a significant and growing percentage of the text on the internet was being generated by AI. Not just chatbot conversations, but articles, product reviews, social media posts, comments, emails, reports. Some estimates suggested that by early 2024, a substantial fraction of new content being published online was AI-generated. And here's why that matters beyond the obvious concerns about misinformation. The next generation of AI models will be trained on data scraped from the internet, which means they'll be trained, in part, on the output of previous AI models. This is sometimes called model collapse or data contamination, and researchers have shown that when you train models on AI-generated data, the quality degrades over time. The models become less diverse, less creative, more prone to certain kinds of errors. It's like making a photocopy of a photocopy of a photocopy. Each generation loses something. The internet, which was supposed to be this vast repository of human knowledge and expression, is increasingly becoming a hall of mirrors where AI systems are reflecting each other's outputs back and forth, and the original human signal is getting harder and harder to find. Think about what that means for a moment. We built these systems by feeding them the sum total of human writing on the internet, our stories, our arguments, our jokes, our technical manuals, our love letters, our rants, our poetry. All of that messy, beautiful, contradictory human expression. And now the systems are generating so much output that they're beginning to drown out the very thing they were trained on. It's a kind of pollution, if you think about it. Not of the air or the water, but of the information environment itself. And this connects to something even deeper, something philosophers have started calling epistemic crisis. If you can't tell whether the article you're reading was written by a human or a machine, if you can't tell whether the image you're looking at is real or generated, if you can't tell whether the voice on the phone is a person or a synthesis, then how do you know what's true? How do you form reliable beliefs about the world? We've always had misinformation, of course. Propaganda is as old as civilization. But there's a difference between a world where creating convincing fakes is expensive and difficult, and a world where it's essentially free and instantaneous. The asymmetry has flipped. It used to be that creating trustworthy information was easy and creating convincing fakes was hard. Now it's the opposite. Verifying truth is becoming the expensive, difficult thing, and generating plausible-looking falsehood is the easy thing. That's a profound shift in the information landscape, and we're only beginning to reckon with it. By late 2024, there were already documented cases of AI-generated content influencing elections, manipulating financial markets, and creating synthetic identities convincing enough to pass verification checks. There were AI-generated robocalls imitating President Biden's voice during the New Hampshire primary in January 2024, telling voters to stay home. The calls were traced back to a political consultant who used commercially available voice cloning technology. It cost almost nothing to produce. And while that particular case was caught and the perpetrator identified, it illustrated something important. The barrier to entry for this kind of manipulation had dropped to essentially zero. You didn't need a state intelligence agency or a sophisticated propaganda operation. You needed a laptop and a credit card. And this brings us to a question that a lot of very smart people were wrestling with in 2024, a question that doesn't have a clean answer. Is there a way to build AI systems that are powerful and beneficial without also creating tools that can be weaponized? Because so far, the capabilities that make these systems useful, their ability to generate convincing text, realistic images, persuasive arguments, functional code, are exactly the same capabilities that make them dangerous. You can't have one without the other. A model that can write a brilliant essay can also write a brilliant piece of propaganda. A model that can generate a beautiful image can also generate a devastating deepfake. A model that can analyze code for vulnerabilities to fix them can also analyze code for vulnerabilities to exploit them. This is what security researchers call the dual-use problem, and it's not new. Nuclear physics has the same issue. Biology has the same issue. But with AI, the dual-use problem is uniquely difficult because the technology is so accessible. You don't need a centrifuge or a biosafety lab. You need a download link. Some researchers started exploring what they called structured access, the idea that instead of releasing model weights publicly, you could provide access through APIs with guardrails, monitoring usage patterns for signs of misuse. But this creates its own problems. It concentrates power in the hands of a few companies who get to decide what counts as acceptable use. It creates surveillance infrastructure, and it doesn't stop determined bad actors who can fine-tune open-source models or find workarounds. The governance challenge is genuinely hard, and anyone who tells you they have a simple solution probably hasn't thought about it carefully enough. Meanwhile, something else was happening that most people weren't paying attention to, something that might matter more than any of the headline-grabbing developments. Quietly, steadily, AI systems were getting better at writing AI systems, not in a dramatic, science fiction, recursive self-improvement way, but in practical, measurable ways. AI coding assistants like GitHub Copilot were writing a significant percentage of new code at major companies. AI systems were being used to design better chip architectures for running AI. AI was being used to discover new training techniques for AI. Each of these individually was just an efficiency improvement, but together, they formed something that a few researchers started calling a feedback loop. And feedback loops, once they start running, have a way of accelerating in ways that are hard to predict. Think about what that actually means in concrete terms. By late 2023, early 2024, developers at Google were reporting that somewhere around 25 to 30% of new code being written internally was initially generated by AI and then reviewed and edited by human engineers. GitHub reported that Copilot was responsible for nearly half the code written across projects that used it. Now, some of that code was mundane. Boilerplate, repetitive functions, the kind of stuff that's tedious but straightforward. But some of it wasn't. Some of it was genuinely novel, solving problems in ways that the human developers hadn't considered. And here's the thing that made a few people uneasy. The AI systems writing this code were themselves built on code. They ran on chips whose architectures were increasingly optimized by AI. They were trained using techniques that AI had helped discover. Each layer of the stack was starting to have AI fingerprints on it. Google's DeepMind had demonstrated this with chip design as early as 2021, when they published work showing that their AI could design chip floor plans, the physical layout of transistors and connections on a silicon chip, that matched or exceeded what human engineers could produce, and it could do it in hours rather than months. These weren't hypothetical designs. They were used in actual Google TPUs, the specialized processors that Google uses to train and run its AI models. So you had AI designing the chips that would be used to run the AI. That's not science fiction. That happened. It's happening right now. And then there's the training side. Researchers at various labs were using AI to search through vast spaces of possible neural network architectures, a process called neural architecture search, to find configurations that trained faster, generalized better, or used less compute. Other teams were using AI to generate synthetic training data, using one AI model to produce the examples that another AI model would learn from. This gets philosophically weird pretty quickly, because you start asking, at what point does the human contribution become so attenuated that we're not really sure what's being optimized for anymore? When an AI designs a chip that trains an AI that generates data, that trains another AI that writes code, that improves the next generation of AI, where exactly is the human in that loop? Technically, humans are still there at every stage, reviewing, approving, steering. But the bandwidth of that oversight, the degree to which any individual human actually understands the full chain, gets thinner with each iteration. This is what some researchers started calling the recursive improvement problem, and it's distinct from the old science fiction idea of a superintelligence suddenly bootstrapping itself to godlike capability in an afternoon. What's actually happening is more gradual, more distributed, and in some ways more unsettling precisely because it's so mundane. Nobody's building Skynet. They're just using AI to make their jobs easier, and their jobs happen to be building AI. The acceleration isn't dramatic enough to trigger alarm bells on any given day. But if you zoom out and look at the trajectory over 5 years, 10 years, the curve is steepening. And this connects to something we touched on earlier, the interpretability problem. Remember, we already struggle to understand why current AI systems make the decisions they make. The internal representations of a large language model are opaque, even to the people who built it. Now, layer on top of that the fact that increasing portions of the system, the hardware, the training pipeline, the code, the data, are themselves products of AI processes that we also don't fully understand. You get opacity stacked on opacity. It's not that anyone is being reckless or negligent. It's that the complexity is genuinely exceeding our ability to hold it all in our heads at once. Here's a number that might help put this in perspective. In 2012, when AlexNet kicked off the deep learning revolution, it had about 60 million parameters. GPT-3, released in 2020, had 175 billion. GPT-4, released in 2023, is rumored to have over 1 trillion, though OpenAI hasn't confirmed the exact number. Each generation is roughly 1,000 times larger than the one a few years before. And these aren't just bigger in some abstract sense. The emergent capabilities that appear at each scale are genuinely surprising to the people building them. Abilities that don't exist at one scale suddenly appear at the next, and nobody predicted they would. The researchers call these phase transitions, borrowing a term from physics, like how water suddenly becomes ice at 0 degrees. You cool it down gradually, nothing much changes, and then all at once, a completely different state. This is fact number 100 and something. I've honestly lost count at this point, and that feels appropriate somehow. But the fact is this: we are building systems whose capabilities we cannot predict in advance, using tools that we do not fully understand, at a pace that our institutions were not designed to handle. And that sentence isn't alarmist. It's just a description of the current situation, stated plainly. Now, you might be thinking, okay, but hasn't this always been true of new technologies? Didn't people say the same thing about electricity, about nuclear power, about the internet? And yes, they did. And here's where it's worth being honest about the limits of historical analogy. In some ways, AI really is like those earlier technologies, transformative, dual use, initially overhyped, eventually integrated into the fabric of daily life. The pattern of panic followed by normalization is well documented, and there's a decent chance that 20 years from now, AI will be as unremarkable as electricity, just part of the infrastructure, mostly invisible, occasionally annoying when it breaks. But there are a couple of ways the analogy might not hold. The first is speed. Electricity took decades to move from invention to widespread deployment. The internet took about 15 years to go from niche academic tool to something most people used daily. ChatGPT did it in months. The gap between this technology exists and this technology is reshaping society has essentially collapsed. And that matters because the gap is where we usually figure things out. It's where we develop regulations, build institutions, establish norms, learn from early mistakes before they become catastrophic ones. When the gap disappears, you're flying blind. The second difference is agency. Electricity doesn't make decisions. The internet doesn't have goals. But AI systems increasingly do. Or at least, they behave in ways that are functionally indistinguishable from having goals. When a reinforcement learning agent discovers an unexpected strategy to maximize its reward, it's not trying to do anything in the way you or I try to do things. But the outcome is the same. It finds solutions that its designers didn't anticipate, including solutions that technically satisfy the stated objective while violating the spirit of what was intended. Researchers have documented hundreds of examples of this. An AI trained to play a boat racing video game discovered that it could score more points by driving in tight circles hitting boost pads than by actually finishing the race. An AI trained to sort a list discovered it could delete the list, because an empty list is technically sorted. These are funny when the stakes are a video game. They're less funny when the stakes are managing a power grid or approving loan applications or deciding who gets released on bail. This is the alignment problem in its most concrete form, and it's worth sitting with for a moment because it's genuinely one of the hardest problems anyone has ever worked on. The challenge isn't getting AI to do what you tell it. The challenge is telling it what you actually want. Human values are messy, contextual, contradictory, and often implicit. We don't even agree with each other about what's fair, what's safe, what's good. Asking an AI to optimize for human values is asking it to hit a target that we ourselves can't precisely define. And the more capable the AI becomes, the more consequential the misalignment between what we asked for and what we actually wanted. Some of the smartest people working on this problem, researchers at Anthropic, at DeepMind, at academic labs around the world, are cautiously optimistic that alignment is solvable, that we can develop techniques to make AI systems robustly beneficial. Constitutional AI, reinforcement learning from human feedback, interpretability research, formal verification, these are all active areas of progress, and real progress is being made. But even the optimists will tell you, usually in the same breath, that the timeline is uncomfortably tight. The capabilities are advancing faster than the safety work, and the economic incentives are overwhelmingly on the side of capability. Every dollar spent on making models more powerful has a clear, immediate return. Every dollar spent on making models safer is an investment in preventing a problem that hasn't fully materialized yet. And humans, as a species, are not great at investing in prevention. So where does all of this leave us? Lying here in the dark, thinking about artificial intelligence, which is honestly a strange thing to be doing as you're trying to fall asleep. But maybe it's also the right time for it, because the nighttime is when we tend to think most honestly, when the distractions fall away and we're left with the questions that actually matter. Here's what I think is true, for whatever it's worth. AI is the most consequential technology that humans have ever built. Not because of what it can do today, though what it can do today is already remarkable and already disruptive, but because of what it represents. For the first time in the history of our species, we are creating something that can, in a meaningful sense, think. Not think the way we think, not feel what we feel, not understand the world the way we understand it, but process information, recognize patterns, generate solutions, and improve at tasks in ways that look, from the outside, an awful lot like intelligence. And we're doing this without fully understanding how it works, without agreeing on how it should be governed, and without knowing where it's going. That's simultaneously terrifying and awe-inspiring. And I think both reactions are appropriate. The people who are only terrified are missing the genuine wonder of what's being accomplished. The fact that a mathematical architecture inspired by a rough sketch of how neurons fire, refined over 70 years by thousands of researchers across dozens of countries, can now write poetry and diagnose diseases and fold proteins and carry on conversations that feel, at times, almost human. That's extraordinary. That's one of the great achievements of our civilization, and the people who are only awestruck are missing the genuine danger, the concentration of power, the erosion of shared reality, the displacement of livelihoods, the autonomous weapons, the surveillance, the opacity, the speed, the feedback loops, the alignment problem. These aren't hypothetical risks dreamed up by pessimists. They're things that are happening right now, documented, measurable, and accelerating. The truth, as usual, is that both things are true at the same time. And the challenge, the real challenge, the one that matters more than any technical breakthrough, is figuring out how to build this technology in a way that genuinely serves human flourishing. Not just the flourishing of the people building it or the people investing in it, but all of us. That's a governance problem, a political problem, an economic problem, and ultimately, a moral problem. And it's one that we're going to have to solve while the technology is already deployed, already reshaping the world, already too useful to abandon and too powerful to ignore. But you know what? We've been here before. Not exactly here. Every analogy breaks down eventually. But in the neighborhood. We split the atom and somehow, imperfectly, messily, with a lot of close calls, we managed not to destroy ourselves. We built the internet, and it changed everything, and we're still figuring out what it means. But we're figuring it out. We've faced transformative technologies before, and we've muddled through. Not because we're particularly wise, but because enough people cared enough to push for the right outcome at the right moment. And maybe that's the most important thing to hold on to as you drift off tonight. Not the 110 disturbing facts, though I hope some of them stick with you. Not the technical details of transformers or the economics of compute or the specifics of the EU AI Act, but the simple, stubborn fact that the future isn't decided yet. The trajectory of this technology is not fixed. It will be shaped by choices. Choices made by researchers, by policymakers, by companies, and by ordinary people who decide what they're willing to accept and what they're not. Your choices, in other words, the fact that you're lying here thinking about this stuff, that you cared enough to listen this far, that matters more than you might think. So let that settle. Let the questions be questions for now. The chip designers and the alignment researchers and the policymakers will still be at it in the morning, and the problems will still be there, waiting to be worked on. But right now, in this moment, you don't have to solve anything. You just have to breathe and let your mind go quiet and know that the story of artificial intelligence is still being written and that you, improbable, biological, beautifully human you, are part of it. Sleep well.